this video, I want to focus on how you can create your own Steam gauges. We aren't going to be using Steam because I have no clue how that would work and how I could implement that. So we're going to be using servos. Servos are like little motors that can be hooked up to an Arduino. They do require a bit more power than your usual device, like a button or an LED. They don't take up that much power. So it's perhaps something to keep in mind that if possible, use an external power source to drive your servos. 5 volts should suffice, and then just hook up the 5 volts. We're going to be looking at how we can take a 180 degrees servo and how we can make it spin something 360 degrees. So all in all, let's just dive in. If you like this content, please leave a like, and if you want to keep updated, subscribe. And I'm going to show, let's just start. As you might see, we have on the right side, we have our 360 servo, and the left side is supposed to be 360, and the right side is 180, sorry. The 181 is already installed, the 361 isn't, because I thought these are MG996R servos. They are great, they are quite a lot more silent than the one that is in here right now. I'm going to give you a sound comparison as well, so you can make an informed purchasing choice for yourself. But there is a version that's 360 out there, they say. Haven't seen it. Thought I bought that one, but this one is 180. So that was a bit of a bummer, but we gotta do what we gotta do. So we have a 181 right here. And as we might notice, I've hooked it up to my potentiometer. Let's see. If you close the potentiometer, 0. And if we open it, it's going to be at 180. And just like I said, it has a range from 0 to 180. So I've programmed the Arduino in a way that it knows that if it's open, it's at 100%, and if it's closed, it's at 0%. So everything in between is in steps of like 1% is 1.8 then? Yeah, exactly. And the battery died. But yeah, where was I? If it's closed, it's at 0. If it's open, 100% is 180. So that's just the range of the servo divided into percentages to make it workable. Go. Now they both are 180 degrees, but the sound is quite different. These are like €2 more expensive, or they aren't that expensive. These are €5, €4 a piece, and the other ones are just a few bucks. So it is a bit expensive, but if you can miss the extra euro, I would definitely recommend doing it, because let's just make a sound comparison. If I hook this one up, it does make sound. Don't get me wrong, it isn't silent. Did I drop something? Oh, yeah, I pulled out Here we go. So I'm going to place it in the same spot as from the camera. It's noticeable, especially if I make fast movements. But it isn't that sound that I personally hate, and believe me, my girlfriend hates it as well if I would have that running all the time. It is dependent on speed though, because if I move slowly, the sound is going to be less. If I move fast, it's going to work harder, it's going to make more noise. So that's something to keep in mind in your design. Soundproofing can be key. If you don't mind, well then just don't bother, right? Why do extra? I already pulled this one out again. Now, how can you hook up a servo? It's actually quite simple. You see 3 colors right here. We have a ground, we have the 5 volts, the red one. So the brown one is ground, can be brown, can be black. Red one, 5 volts. Yellow one is the one that's going to your Arduino. And that's the pin where you send the commands to, like how far you want the servo positioned. The beautiful part about a servo is it always finds a way back home. So what I mean by that is that if you rotate it and you say go back to 0, it always goes to the same spot. And I've got an example to show you why that is and what the difference is with a stepper motor, because those are actually a lot more quiet. But in our application it's more easy to use the servo. These were cheaper? Man, I don't know actually. Don't pin me on that, but it's easier to use to find home, and I'm going to show you why. I'm also going to show you how you can take a 181 and create a 361. So let's go over that, and then we go back to our code to see how we can actually implement this with our fuel. Now, to get a clear look on why it is that we only can rotate 180 degrees, I've unscrewed one of my servos, the MG996R1s, to give you a closer look on how they look from the inside. Because you see that's the top part, and then we have the bottom part at the bottom. And one thing you might notice is that there are a lot of gears in it. And that has a proper reason, because the device you see on the left, so not the golden one, but the silvery one, that's our motor, and the golden one on the right is actually a potentiometer. Now, as we might have noticed from our own projects, a potentiometer also has a certain range of motion. It can't keep rotating. Let me see if I can get something in there so you can get a proper look. It's in there quite sturdy. But you might, yeah, it's a bit hard to see, but that's the downside of the potentiometer. I hope I can get focus on it. Here we go. Yeah. So we have on the left side, we have our motor, and on the right side, we have the potentiometer. Like our previous projects, a potentiometer has a certain range it can rotate. So once the motor is at the max of potentiometer, it knows its position. It will pass you that value. That's why you say write, and servo, I'm going to write you this value. It knows, okay, this is my potentiometer. This can read the value that its current state is currently at, and if I reach that value, I must stop, and the other way around. So this is a normal potentiometer. They look quite similar actually, not that different. And just like the potentiometer in a servo, I can't rotate it. Now let me grab the other motorized solutions we have. We have a stepper motor as well, and we have just the servo motor we have been running all along, but without potentiometer on it, because that's just the left part of a potentiometer. It's what you see in my left hand, and a stepper motor is what you see in my right hand. Now the left one doesn't know, just goes on or off. It doesn't know when it's reached a certain point, so we can't really use it to accurately represent the value on a gauge, right? That's the beauty of the servo with the potentiometer, like you see in the right. It's just a motor, but with a good indication of its position. Now a stepper motor has also a good indication of its position in a way that it knows exactly how many steps it took forward or backwards. It has no home position, so if you unplug it, the home position wouldn't be concise. So if you stopped halfway and next time you told it, okay, I need you to make 10 steps, it will make 10 steps, but it will be from the point where you left and not where you started initially. It will be driven by a board, and depending on which one you get, it will take certain steps. Just like a bit like a rotary encoder. It also clicks like click, 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 click. That's the same way a stepper motor works, kind of. Not really, but the same concept. So if you would want to use this, you would actually need some way to measure if the meter is at base position. Let me quickly show you a video of my 3D printer. So, first of all, let me say I'm sorry, I need to dust this thing off. But a 3D printer uses stepper motors. It has 1, 2, 3, one in the front to move it on the x-axis. So in theory, it shouldn't be able to know when it's at home position and your prints would always come out inaccurately, right? Well, they found a fix to mitigate this flaw in the stepper motor, and that's, you can see there's a little button there that once the extruder reaches the left, it's gonna hit the button. And now the system knows, or the device knows, okay, I'm at home position, calculate my steps from this point forward. It has one on the left and one at the bottom, and then it goes up and to the right. For the approach that I've chosen, we need a few things. We need a servo and we need 2 gears. It's important to have a bigger gear hooked up to the servo, or at least somewhat hooked up. I had it glued on with a hot glue gun, but I have the worst hot glue gun out there. It was €3, and let me tell you, it was not worth even €1, so got another one coming, so I hope it will stick on better then. I'm gonna perhaps make it stick with something else later on. But we need a bigger gear on the servo and a smaller gear. I've mounted it on the plate just as a demonstration purpose, but it's going to be used to alter your gauge, so you can place it anywhere you want your gauge to be. So I'm just going to show you how we can calculate what kind of gear we need and how you can use this to convert a 180-degree servo to a 360-degree servo. And by the way, I've got this currently just hooked up to a button to show you that every time I press it, it will rotate X amount to actually see what the results will be. So the first thing that's important is the amount of teeth on the big wheel. So in this case, I'm just going to count them by putting dots on them, or else I'm going to lose count. Okay, so now we know that the big wheel has 57 teeth, and we're going to do the same with the small wheel and see how many teeth this one has. Okay, so we know that the smaller gear has 14 teeth and the bigger gear has 57 teeth. This will already tell us that, because we could only see it, but this on paper will tell us that the bigger gear will increase the amount of rotations towards the smaller gear. We're going to call the bigger gear the driving gear, and how we're going to call the smaller one, I have no clue. Just call it the smaller gear for now. So we can use these numbers to actually calculate how much the bigger gear has to rotate for the smaller gear to rotate once. Or the other way around, if you rotate the big gear once, how many times the smaller gear will rotate. We can achieve this by dividing the amount of teeth on the big gear by the amount of teeth on the small gear. So in our case, it would be 57 divided by, and if we would do that, the result would be something around 4.07. So that's the number that will tell us if we rotate once, how many times the small one will rotate. So it has a ratio of 1 to 407. So if we rotate twice, the small wheel will rotate 8.14 times. And that is actually giving us a solid number to calculate how much we need to turn to convert the 180 degrees on the servo towards the 360 degrees we want on our arm. Now, to get the proper number, we need to take the 360 degrees we'd like and divide it by the ratio we've just calculated, so the 4.07. This will tell us how many degrees the big wheel has to turn. This would leave us with a value of around 88.45. So a rotation of 88.45 degrees on the big wheel would mean it would rotate 360 degrees on the... Now I've programmed the servo to make incremental changes of 8 degrees, and I put a little dot so we can see if the smaller gear will actually rotate 360 degrees opposed to the 88.45 degrees on a big gear. So as you might see, if we place it on the servo, it's a bit finicky because it isn't on really good. I hope we don't make it. So there are two options. A, I've miscounted the teeth, or B, I've miscalculated the equation. And the main cause of our problem were the amount of teeth. Because it weren't 75, it was 74 teeth. And this would result in 74 divided by 14 is a ratio of 3.35. So I've altered the code to make it so that we are going to change 107 degrees instead of 88.45. I'm very sorry for my very crowded drawing and explanation right now. So always good to double count your gears, teeth of the gears to make sure that you're correct. So let's put it in the beginning. I'm going to reset the servo. And if we rotate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and it should, yeah, exactly. So this is what we were after. We've converted 107 degrees on the big wheel to a constant 360 degrees on the small wheel. And this will give us an indication on how we can use a 180 degree servo to get a 360 range of motion on our gauge. So if you would like to have this is a way to do it. And this will leave you with a happy face. So for this to work, we need a few things. We need our connector, which can be downloaded from www.bitsandroids.com/downloads. And it's the version 0.5, so perhaps you already have it. If not, you can go to the link in the description. And then we can select the selected quantity of fuel in percentages. Right now it's just overall percentages of the fuel, but I have it already in the pipes to have the left tank, right tank, middle tank, all the tanks you can dream of, to get those individual values as well. I will update it later on and release a new update. I will make a video, but probably the updates will be faster than the video. And in the upper right corner, it will just say a new version 0.5.2. So keep watching that. If you want to keep updated by video, subscribe, and I will let you know when it's out. We need to select the COM port. Well, the game is still updating, so I'm not going to start it yet. We're going to look at the code first. We need our Arduino library, which can be downloaded from the same link. For testing purposes and debugging, I've included an LCD screen and the wire.h library. If you don't want that yourself, you don't have to include it. It's just something I found handy to see the values that were coming in. And we need the servo.h library. I believe this one comes already packed with the Arduino IDE, so you don't have to go out and download that yourself. If you don't have it, you can always go to include tools. All right, I'm in the wrong place, right? Yes, I'm totally in the wrong place. It's in Sketch, include library, manage libraries. And then we'll pop up this window. And here you can just look for servo. Something is going wrong. Oh, here we go. In my case, it's already installed. I see there's an update available. So if you want to keep it updated, you can update it, but you know where to find it at least. Well, we've got our servo hooked up to our Arduino, and we know at which ports. We're just going to start by saying int servo pin is, what was the servo pin? I have it written down somewhere. Let me see. Oh, 35. quite a high number. Here we go. We're gonna get a value from the game. So we're just gonna declare an int val is 0. We could just also do this, by the way, int val. And we're gonna have an int old val. Now, why is it important to have an int old val? It's because if we don't do that, we're gonna send Arduino the current value every time the loop gets executed. And because the servo actually makes noticeable sound, I like to make sure that we only send data and risk that it starts moving if it's an updated value. This is to make sure that A, you don't send unnecessary commands towards the servo, and B, just to make sure that it stays quiet and doesn't update anything if it doesn't have to. So we're going to check if the old val is different from the new val. If that's the case, send something. If that's not the case, we're not going to send anything. So in the setup block, we're going to do my servo. Oh, no. We first need to declare my servo. So we go above the setup block. We're going to say servo, my servo. And then in the setup block, we're going to say my servo.attach. I'm going to attach it to the servo pin. So in this case, pin 35. Now in my case, I want to add an LCD screen. So I'm just going to copy paste it. Once again, this is just to show you what is happening. You don't need to have that in the same library if you don't want to. So we do lcd.init and lcd.backlights. So now I've initiated it and we turn the lights on. Now in the loop, what are we going to do? Like I said, the game is updated, so I'm going to start it up. We're going to receive a value, the selected quantity in value. So we could do val is connector dot get fuel percentage. Now I'm going to actually have to take a quick peek if that's the correct terminology used. And I'm going to put the code down in the description as well, or at least a link to the code, so you don't have to go into the description and figure it out yourself. There will be a link where you can go to download this code for yourself, so you can have an example on how to use it. I was checking. Okay, so the function is called get fuel total percentage. So we can close that again, and I'm going to update this as well in the post so you are up to date on what the latest term is, or the latest function call. There's a new one, and it will return a value in percentages as an integer. So it will already just send us 100, 99, up to 0, without the decimals in between. Now, we know the number, so we're going to say if val is not equal to the old val. Let's just give the old val a value already. It's going to say -1. And we're going to do something. Now, why did I choose -1 as the starting value? It's because if this would be 0, and we're going to check if the current val is not equal to the old val. So what if we started a plane with no fuel in it? Then it would be 0%, and the old val would be 0% as well. This would result in it always being not true. Now we can't start a plane with -1% fuel, right? It's empty, so it's 0. So there is nothing beneath empty. It isn't like you owe somebody fuel. Perhaps you do money-wise, but we don't express that as a -% fuel. That's why I'm gonna go with -1. I don't know how I did this, but with -1. So you always know that the first value that comes in isn't equal to the old value. Still with me? So if it's not equal, we're gonna say my servo.write, and we're gonna write the val. Now, if it's not equal, we want the old val to become equal to the new val. So if it was different, we're gonna store the new val as an old val, and the next value that comes in, we're gonna check again, okay, that was our new old val. Yeah. Is this val once again not equal to the old val? Then update. If it's equal, so nothing's changed, don't update. So that's the point. The software already only updates something when something has changed, but because we're in a loop, the val will get requested from our stored library. So it will say, give me the value every time this gets executed. So that's why we still need the failsafe to make sure that the servo is a lot more quiet. So if we would do this, and let's just do the lcd.print val, set the cursor at 0.lcd, set the cursor 0. This would already be enough to make our loop work. Let's just add a little delay just to get things a bit more stable. See, old val, yeah. Let's upload the code. Got that hooked up to my Arduino Mega that's in it. And let me quickly show you what is happening. Okay. So let me get this camera. Here we go. I feel completely stupid because we were almost done, and then I've been troubleshooting for 2 hours until I remembered that for the Arduino Mega, you need to put the capacitor between the reset and the ground. I've been working with Leonardo for quite some time, so I totally forgot that this was a thing, that if you send serial communication towards your Arduino, you do need to have the capacitor in, or else it will keep resetting. And that is what was happening. Because this device is new, I rewired everything just a minute ago to check if everything was okay, until I realized the issue was just the capacitor. But let's get back to track, because as we might see right now, it's at 0 and 100%. So if we now start moving the fuel, we can see that the arm is moving as well. Right now I've put in from 0 to 180. If you want to decrease the range, like I think it's something around 20 until 160, you can change the value to the code I'm going to show you in a second. But as you can see, it's quite responsive. And it's changing on the screen as well. I see the upper part is the percentage, but I flipped it around, so it's actually 79, so that's 21. No. Well, the bottom part of the percentages, and the top part is the degrees. So it can be correct, yeah. It is. Is it correct? Let me see. Oh yeah, it are the degrees, but it's counting from the right side instead of the left side. So that's, see, this is 180 degrees, 0%. This is 0%, 0 degrees with 100%. It is because my servo is flipped upside down. Not a big issue, but then the number is off, so you need to change the calculation. So what did I do? We have our connector, like we said before. It starts the connection. So if data is coming in, do something. It's going to receive the fuel total percentage, and it's going to receive it as a string. So we need to convert it to an integer, to make it so we can do calculations with it. Now, okay. So pay close attention, because my servo is upside down. I need to do 180 minus 180 multiplied by the value divided by 100.0. So what are these numbers? This is the max range. And because it's upside down, I need to go the other side around. So 180 minus. And then I do the 180 degrees, multiply it by the value that came in. So let's say 77 came in, so 77%. Well, we can't multiply 180 by 77 because that would be way too high. So we do 180 times the value divided by 100. So 77 would become 0.77. And then we get the proper number. It's important to have the .0 in the end to make sure that it will calculate as a float and not as an integer, because then you get 0 all the time. So that's the math behind it. What we then do is we go to if the new value is not equal to the old value, so we have that step. We do servo.write, so we write the percentage of the rotation you want. Old val becomes new val, and here I just print it out on screen so you can actually see what is changing. Now, this is all there is to it actually. You have a servo, you have, in my case, an LCD, not even necessary. And we just receive the percentage from the game. We can change it. It will change the arm based on the calculation you make. Now we've been working with fuel. Once I've added more data types, or perhaps you can already make something for the, how do you call it? The airspeed, for instance, or the altitude. It's the same principle. It's getting dark already because I messed up. But as always, if you have any questions, let them know in the comments down below. If you liked it, leave a like. And if you want to keep updated, subscribe. Once again, this was quite a basic solution, but it looks cool. It feels cool to have. So it's you know, that's the beauty about these projects. They're this small, but they can make quite a big improvement on your game, or even if your friends come over and they see an actual working gauge on your desk, they're gonna be like, what's that? And that's because it looks way more impressive than it behind the scenes is, but you don't have to tell that to your friends. So once again, thanks for watching. If you have any questions, let me know, and I'll see you in the next one.